Hello and a very good day. This is an introduction of our case study. This reliability and maintainability study focuses on a natural gas processing plant with a daily input of 100 million standard cubic feet split equally between medium pressure and high pressure streams. The facility processes raw gas into pipeline quality fuel through separation, compression, acid gas removal, dehydration, and NGL recovery units. Over the past 5 years, the plant has experienced declining performance due to frequent equipment failures and extended repair durations, impacting reliability, availability, and maintainability. The study aims to evaluate system performance using historical failure and repair data, identify critical equipment, and propose engineering strategies to achieve a target availability of 99% using Weibo++ and BlockSim for statistical modeling and simulation.
This brings us to the project background. Our objective was to conduct a comprehensive ARAM or asset reliability, availability and maintainability study on this natural gas plant. We chose ARAM because it's essential to ensure reliability or failure-free operation, maximize availability, targeting 99% of uptime, and improve maintainability, meaning faster, easier repairs. The plant goal is to transform raw natural gas into pipeline quality gas by removing impurities. To support this, we analyzed 5 years of failure and repair data using Weibull and BlockSim. We especially focus on identifying bad actor, equipment, units that frequently cause downtime or performance drop. Failure in components like compressor and separators can lead to production losses, extended downtimes, and even environmental and safety risks. From this study, we achieved several key outcomes: a more optimized maintenance strategy, improved operational efficiency, lower downtime and environmental impact, and more sustainable, resilient energy operation.
Next, the problem statement of this project, we focus on a gas processing plant that has been experiencing recurring breakdowns and extended repair durations over the past 5 years. These operational issues have directly impacted the plant's performance in terms of reliability and availability. Despite industry standards expecting 99% availability, the current performance falls short of this benchmark. Upon reviewing the system, certain equipment known as bad actors were found to be consistently responsible for a large portion of the downtime. Furthermore, the plant still relies heavily on reactive maintenance strategies, which do not address the root causes of failure. Therefore, a structured RAM analysis is essential. By using tools like Weibo++ and BlockSim, we aim to assess system performance, identify weak points, and propose effective strategies to enhance reliability, availability, and maintainability.
Moving on to the project objectives, this project aims to enhance the reliability of a gas processing plant. So, we will first develop a detailed reliability plot diagram (RPD) and conduct RAM analysis using 5 years of operational data. Next, we will perform criticality assessments with DTCI scoring and run Webull++ and BlockSim simulations to evaluate the system behavior. And finally, we will recommend engineering and maintenance optimizations to achieve 99% availability, improve sustainability, and to ensure long-term asset integrity.
Next, I will explain the distribution type and parameter of equipment for analysis. In reliability engineering, selecting the correct statistical distribution is essential to accurately model failure and repair times. For this analysis, we use several distribution types, depending on which best fit the historical data. Each distribution has its own parameter. Log normal 2p use log mean and log standard deviation. Normal 2p use mean and standard deviation. Variable 2p use beta and eta. And lastly is exponential 1p use mean time. The table on the left shows the selected distribution and the corresponding parameter for both failure times and repair times for each equipment, like separators, compressor, filter, and so on. To determine the best fit distribution, we follow this step. First, insert data for the failure times and repair times one by one. Click the distribution wizard and then click Analyze to get the best distribution type. And lastly, click calculate and copy the data parameters for each component.
This model represents the entire processing flow, from the raw gas intake all the way to sales gas output. The plant handles 100 mmscfd, divided equally between medium pressure and high pressure gas streams. Each block here symbolizes a critical unit or equipment such as separators, compressors, chillers, and reactors. These are grouped by function into several major units. The higher pressure and medium pressure separators units initiate the process by separating liquids from the raw gas. Then the feed gas compression unit boosts pressure for further processing. The acid gas removal unit, followed by the amine regeneration and sulfur recovery units, eliminates H2S and CO2. Next, dehydration unit removes water vapor using molecule sieve beds. Finally, the natural gas liquid (NGL) recovery unit separates valuable hydrocarbons, and the gas is cooled and sent to the sales line. By using this block-based structure, we can identify how equipment failures can affect overall system reliability and availability.
In this slide, I will explain about the average availability of natural gas processing plant for 5 years data. To evaluate plant's overall maintainability and availability, we use a RBD reliability block diagram approach. Each block in RBD represents a key component or subsystem in the plant. The first step is double-click each box in RBD to configure the equipment block. Then, we click the plus icon to input two models, one for reliability and another for corrective tasks. After that, we enter the parameter data, including failure and repair distribution for both reliability and corrective action based on our earlier analysis. Next, we repeat this process for every block in the plant system to complete the entire RBD model. And finally, we run the maintainability and availability simulation for duration of 5 years with result output every 6 months. As shown in the simulation window on the right, the plant average availability over the 5-year period is about 24.84%. The figure helps identify the system reliability performance and highlight the need for improvement in high-impact components to boost availability.
Now, we take a look at the downtime, throughput, cost, and impact list, or DTCI, where the ratings from 1 to 3 were given in accordance to the severity of the parameter. The total ratings were used to classify the equipment into their priority, where critical priority were marked in red, high in orange, medium in yellow, and low in green. It is observed that compressors, turbines, and reflux drums are the identified critical equipment. Compressors scored the highest with a DTCI total of 12 and follow a Weibull distribution with a shape factor of 1.86, indicating wear-out failure behavior. This means that the reliability degrades over time, making them ideal candidates for age-based preventive maintenance. Now, despite a short repair time, their frequent failures and high impact on the throughput make them a top priority. Turbines also scored 12 and follow an exponential distribution with a mean time to failure of 5.47 hours, suggesting random failure behavior. Their low availability and unpredictability require real-time monitoring and rapid intervention and strategies. And lastly, reflex dump with a score of 9 also exhibit exponential failure behavior, but with longer repair durations, increasing their operational risk, especially in critical process units.
To reach 99% plant availability, we will focus on five key improvements. First, we'll implement targeted maintenance using preventive and predictive methods to reduce equipment failures. Secondly, system redundancy will be added with backup compressors and turbines for uninterrupted operation. Thirdly, we will optimize repairs and upgrade designs to reduce wear and speed up maintenance. And the fourth one, advanced monitoring and analytics will enable smarter repair and shutdown decisions. And finally, we will train a skilled workforce to boost repair efficiency and minimize errors. Together, these strategies will enhance reliability and overall plant performance.
In conclusion, based on our RAM analysis, The natural gas processing plant currently operates at an availability of only 24.84%, which is significantly lower than the industry target of 99%. Through simulations and DTCI critically ranking, we identified compressors, turbines, and reflux drums as the most critical equipment contributing to frequent failures and prolonged repair times. To improve this, we recommend implementing predictive and condition-based maintenance strategies to catch failures early. Adding system redundancy such as backup compressors can also reduce production downtime during equipment failures. Additionally, design upgrades and better spare part planning can help improve maintainability and reduce repair times. Integrating real-time monitoring tools will support better decision-making, while investing in technical training will improve the efficiency and accuracy of maintenance work. With these improvements, the plant can move toward achieving the 99% availability target, improve production reliability, and ensure long-term operational sustainability.